Hello, everyone. In today's presentation, I will present our paper entitled IMG-DNA Approximate DNA Storage for Images. So in today's presentation, I will cover the motivation of this work, DNA background, our contributions, and also I will introduce the image DNA schemes and show the experiment result. So finally, I will conclude our work. So for the motivation of this work, today we are living in the big data era. Based on the report from IDC, the data is doubled almost every 2 years. So last year in 2020, the total amount of data in our world is about 44 zettabytes. And 4 years later, in 2025, the total amount of data will reach to 175 zettabytes. So this is a huge amount of data, and we need to store all those data in the storage system. So among all those data, the images is one important type of data, and we do have a high demand for storing those data. So as reported from Twitter, Facebook, and also other IT industries, so every day we generate a lot of images. So as indicated in Twitter, so there's about 3,000 images are uploaded per second, which is equivalent to 200 gigabytes data. And Facebook also have about 315 million new photos each day to be uploaded into the Facebook. So according to that, there's a critical question is how to efficiently store those images. So there's one emerging storage devices, so-called DNA storage, which has high spatial density and also long persistencies. So a theoretical densities of DNA storage is 455 EB per gram. And also in DNA storage, we can store data for 100 years. So this is the advantages of DNA storage. But DNA storage also have one disadvantage, which is error prone. Regarding to the images, so we have a lot of image data generated every day, but for images, it's kind of fault tolerance, which means even we have some errors in one image, but we still can recognize these images. So in this paper, we try to answer the questions of how do we efficiently store images in DNA storage. So before going into the details of this paper, I want to introduce the background of DNA storage, and also we'll cover the background of images. So for the DNA, basically there's four basic elements, A, T, G, C. So normally A and T are associated with each other, and C and G are bonded with each other. So in DNA storage, there's four major steps: encoding, synthesis, sequencing, and decoding. For write operation, including encoding and synthesis, people try to convert the binary digit like 0, 1 into DNA format, which is ATGC, and then they will synthesize those DNA sequence into DNA. So for the read operation, people just based on the sequencing machine read out those DNA sequence, and then according to the encoding scheme, they decode the data back to binary digit. Here is one example of DNA storage encoding. So in that paper, people use the binary data, and then according to Hoffman encoding, they convert the binary data into base 3 values. And after that, they use a rotating encoding to convert the base 3 value into nucleotides or DNA formats. And after that, they chunk the data into a small chunk, and also they add primary index or other metadata information to the payloads. So here are the one details about the rotating encoding schemes. So the rotating encoding schemes is based on the current ternary pattern and also last nucleotides. So for example, if we have the current ternary pattern 0 and also have last nucleotide A here, then the new nucleotides will be generated based on this table, which is C. So the reason of using rotating encoding scheme is we can avoid long homopolymers like AAA in the DNA storage. So such long homopolymers in DNA storage will cause a lot of really high error rate, so which is not good for us. And but based on the rotating encoding manner, there's one observations in the DNA storage, which is so-called error propagations. So the error propagation indicate one nucleotide error can cause a series of errors in its subsequence. So I see in the right side example here, for example, if we have some errors, deletion errors at the third row here, so which means we cannot read the nucleotide C out. And then the rest of the nucleotides will be left shift one nucleotide. And after decode, we will totally read the wrong data. So compared to the decoded binary value and original binary value, we can see only the first bytes data are correct, but the following bytes data are totally wrong. So this is so-called error propagation, which only one error in the nucleotide or DNA sequence can cause a series of errors. So here I want to introduce the background of images. So in this paper, we use JPEG-based images, but for other type of images, we may have the similar conclusions, but we will leave for the future investigations. So according to the encoding process of JPEG-based image, first of all, we divide one image into 8x8 blocks, and then those blocks will go through the DCT quantization process. Both DC and AC coefficients are generated from the quantization, and then DC will go through DPCM process, and AC will go through zigzag and RE process. So both DC and AC coefficients finally will encode it based on the Hoffman encoding, and finally they will store in the GFIF format. So there's two observations from the JPEG-based images. One is those images are fault tolerance, as indicated previously. Even we have some errors in the images, but we still can recognize all those images. And also the DC-AC coefficients have different influence on the qualities of images, which means DC and AC have the different sensitivities to the error. So according to the observations from the DNA storage and also images, here's our contribution. So based on those observations, we propose image-based DNA storage architecture to improve the robustness of DNA storage. So based on the observation from images, we do AC-DC coefficient separation at DNA level, and also use so-called asymmetric barriers for AC-DC coefficients to reduce the overhead. And also we proposed to add barriers into DNA storage to prevent the error propagations. So in this slide, we show the overall architectures of image DNA. So basically there are four major steps. First of all, we do have the binary level AC-DC separation based on the JPEG-based encoding process. And then we will encode all those binaries into the DNA sequence. So for DC and AC coefficients, we will separately encode them into the DNA sequence. After that, we will separately add barriers to AC-DC coefficients. In here, we add dense barriers for the DC coefficients and add sparse barriers into the AC coefficients. Finally, we will chunk the data from a long DNA sequence into short DNA sequence, and also we will add the primer index and other metadata into the payload to construct the multiple DNA strands. So according to the adding barriers and the symmetric barriers, basically we use AA as a barrier indicate to separate the partitions. And the barriers can restrict the error propagation in a partition. And the reason here is we can use A as a barrier indicator because there's no two consecutive identical A's in the rotation encoding schemes. And also we use a barrier window to prevent the insertion and deletion errors. For example, if we have some insertion errors happen and generate a new AA here, but when we use the barrier windows, we just consider the AA as a barrier indicators inside the barrier window. If there's one AA outside of barrier window, we just ignore that. And moreover, we also use so-called asymmetric barriers, which is we apply different partition lengths for AC/DC coefficients. So from the quantities of images point of view, AC/DC have different influence, and we want to insert more barriers into DC to reduce the error effect. And from the overhead point of view, the number of the ACs is larger than that of DCs. So we want to reduce the overhead of adding barriers into ACs. So here, by doing that, we can achieve the similar encoding densities as the traditional DNA storage. So according to the experimental setup, we use the IMG-DNA as our data set, and we use the 3 schemes to compare it in our paper. The raw DNA is the traditional DNA storage. Approximate image is the one type of approximate storage schemes normally used in the solid state drive, and the IMG-DNA is our proposed schemes. And we use the one matrix so-called SSIM to indicate the qualities of images. And we use 215 base pair for the DNA strand length. So in our experimental environment, we use a system with CPU at 3.6 gigahertz, and the memory size is 8 gigabytes. And the software tool is MATLAB 2020. So here we just show the overall comparison between 3 schemes, and we indicate we inject a different error rate among 3 schemes, and based on the result, we can see our scheme achieved the highest average SSIM, which means we achieve the highest qualities of images. So we also show a graph views of images with different encoding schemes. So here, as compared between those images, we can see our proposed IMG-DNA achieved the images which very close to the original one, but for the approximate DNA and also raw DNA, their figures or their pictures are quite unclear. So we also have more data as shown in the paper. For example, we investigate the influence of other factors like the partition length and others. So if you have interest, please go to the paper for those more information. So here are the conclusions of our work. So we propose an image-based DNA storage architecture called IMG-DNA to improve the robustness of DNA storage. So according to the observation from the DNA storage and also the images, we propose to use AC/DC coefficient separation at DNA level, and also we add the barriers to prevent the error propagation scenarios in the DNA storage. Due to the different sensitivities, we use asymmetric barriers for AC/DC coefficients. So according to the experimental results, the proposed scheme achieves much higher robustness than other studies. So this is the presentation, and thanks for watching my presentation. I'm happy to answer any questions related to this paper. Thanks.
Thank you, Bingzhe, for the nice talk. So we have a question from the Slack channel from Rihu. So could you unmute yourself to ask the question?
Hi. So I have a question that I wanted to know, like how we are doing the chunking of the strands.
Okay, so thanks for your questions. Basically, the chunking size is related to the DNA strand length. So normally we have like 200 base pair for one DNA strand due to the limitations of sequencing machine. So basically, based on the encoding densities, we convert to say, okay, maybe we just chunk the binary data into 300 bits or maybe 215 bits. So I don't know whether I answer your questions. Yeah. So basically we do the, yeah.
Mm-hmm.
Go ahead.
Sorry, please go ahead.
Oh yeah, so basically after like we encode the binary data into the DNA format, and then we just calculate, okay, how many nucleotides we want to chunk, and based on the chunk size, we just chunk the DNA and then go through the synthesize process to like synthesize the data into the DNA. Yeah.
Okay, thanks.
Yeah.
And I have a last question that just wanted to know, like whether this was done in a wet lab experiment or it was in silico.
Yeah, basically this is based on the simulation. Yeah, so we will do the wet lab experiments in the future. Yeah, but for the simulation, it's true, it's kind of has some limitations, but it's kind of common method in the biology field. For example, people use like the BLAST or some other simulation tools to check the violations or some other things based on the primer design rules and also the payload rules. Yeah. So it's kind of common technologies used in the bio field to reduce the cost. You know, when we do the wet lab, when we synthesize the data into the DNA, it's really expensive. Yeah. Right. But it's a good question. Yeah. Thank you.
Thank you. Thank you for your answer. Thank you.
Thanks for the question. So a follow-up question on the simulation platform. You know, DNA storage is a relatively new area, and I'm wondering, you know, for the general computers researchers, you know, who are not expertised in this area. So could you elaborate a little bit more, you know, on your experimental setup and what kind of, you know, simulation or emulation platforms are there available, you know, for researchers who wants to get started, you know, with research in DNA storage?
Okay, so actually I have the background of the computer science and also electrical engineering. I'm not a guy from the biologic. So if you want to like go into the research on the DNA storage, first of all, I think you need to read some papers about the bio stuff. So, or maybe you can, you may have some guys from the bio side to tell you some basic rules of the DNA storage. For example, there are some constraints and also the encoding schemes, what kind of pattern you need to use. For example, as mentioned in the paper, we cannot have like long homopolymers because when we have like AAA in the DNA storage, we cannot read the data correctly out based on the sequencing machine, right? After you have such kind of basic background, I think you can base on some paper to do the simulator by yourself. Like I think there one slide is mentioned in the presentation. There's one encoding schemes. So you just follow the step of the encoding scheme. You can, whatever languages you can use, like Python or MATLAB or C or C++, you just follow the process to like encode the data. But also there's some like constraints, bio constraints you need to follow to check whether those the synthesized or encoded data cannot violate any bio constraints. Yeah. I hope I answer your question. Yeah.
Yes, definitely. Thank you so much for the answer and the nice talk and work. So I hope to see, you know, many more research groups will work on DNA storage and hope to see, you know, more research from this direction.
Okay.
All
thank
right.
you.
Thank you.